Hey everybody, this is a demonstration of a electrochemical potential, so the transport of an ion across a membrane. This is a sort of calculation that's, I would say it's more bark than bite. You see an equation, you see a delta psi, and it's all of a sudden like, oh man, this is tricky. This is a tough one. But I assure you, it's not that terribly difficult of a calculation. So what I'm going to do right now is I'm going to share my screen with y'all, and I'm going to show you just kind of a question that I came up with on the fly here. Share screen, done. Okay, so the first thing that I'd like to draw your attention to is this equation right here. This equation is delta G equals RT, natural log A over D, or I'm sorry, A over S plus Z, Faraday's constant, times delta psi. Now, this equation quite simply can be broken down into two different parts. The first part is a chemical potential. The second part is an electrical potential. Hence, this is a electrochemical potential calculation. Now, your delta G is the free energy of this reaction. To set the stage for this equation, or to set the stage for this, what we've got are chloride ions that are moving from the exterior to the interior. So we've got our lipid bilayer here, we've got Cl out here, and we are moving them inside, okay? Now, what we're going to do to solve this problem is we're going to look at the two different parts of this equation. The first part of this equation is that chemical potential. The second part is that electrical potential. Now, the variables that I have here that are important are delta psi is the membrane potential. That's negative 90 millivolts. And just a second, I just need to do one minor thing. I'm going to rewrite this in terms of volts. And so that's going to be the same as negative 0.09 volts, okay? Faraday's constant is 96.485 kilojoules per volt mole. And then my R value is 8.315 times 10 to the negative third, which I forgot to write, the times 10 to the negative third. And so that's going to have a significant impact on my answer. So I'll write that times 10 to the negative third. Kilojoules per mole Kelvin. My temperature is 37 degrees Celsius. And I believe, oh, and then the last thing that I need to worry about is my Z value. And that is the charge of my ion, which happens to be -1. Okay, so there's everything that we need, but let's go ahead and tackle the chemical potential portion of this reaction first. So I'm gonna go ahead and give myself a little boxed off space here. I'm gonna try to, yeah, there we go. What I'm going to do is I'm going to ask myself, is the movement of these ions from the exterior of the cell to the interior of the cell, is that a favorable movement? Now, simply from a, well, one variable consideration, you can look at it and you say, yeah, it looks like it's going to be. And the way that you can do that is by looking at the concentration of chloride ions outside of the cell and the concentration of chloride ions inside of the cell. Those numbers are given right here. We have an exterior concentration of 125 millimolar and an interior concentration of 25 millimolar. So what that means is those chloride ions are going from outside, where there's a high concentration, to inside, which I've already kind of drawn that here. So I'm going to write 125 millimolar. There's a ton of them out there, and there's a small number of them on the inside. And so that's where we want to send them, basically. Now, the reason that you can't say right off the bat, oh yeah, we're good to go, is because at different temperatures, you might see a different result. But let's go ahead and plug this in. So my R value is 0.008315. I just went ahead and wrote that not in scientific notation, so I can look at the magnitude of that number. That's my R value, times my temperature, which is 37 degrees Celsius, which is the same as 310 Kelvin. Then what I'm going to do is multiply that by the natural log of the concentration of my substance in the destination, which in this case, the destination is on the interior because I'm sending my chloride ions from the outside in. So their starting point, their source, is the exterior. So what that's going to look like is natural log of 25 divided by 125, okay? So when I plug all of this in to my calculator, and the way that my calculator works, I have to do 25 divided by 125, then press my natural log function or my natural log button. What that's going to do is that gives me a value that is negative 1.609. Okay, so that should be an indication, looking at the rest of these numbers being positive values, well, chances are that my value is going to be negative overall. But let's go ahead and, for the sake of thoroughness, let's go ahead and plug these other numbers in. So negative 0.1069 times 310 times 0.008315. And that gives me a value of negative 4.14, I'm going to call it 0.149. 0.149, and my units for that are going to be kilojoules per mole, because I had the temperature factored in, and now that's gone. Okay, now that's the chemical potential. So the chemical, or from a chemical standpoint, this is a favorable movement. From an electrical standpoint, is it a favorable movement? What I need to do in order to calculate that is I need to plug in all these different values. My Z value, my charge of my ion is -1. So if you had something like magnesium or I don't know, a nitride ion or something, you'd have a different value there. But for this, it's just -1. Okay, and Faraday's constant is 96.485 kilojoules per volt mole. And I'm going to multiply that by delta psi. Okay, now this is the place where lots of people get mixed up. And they say, oh no, I don't know what to do. I've done it wrong or something like that. That delta psi value is going to remain the same, because this delta psi value is going to be presented from the vantage point of moving from the outside to the inside. Now, in the event that you talk about something moving from the inside to the outside, then you need to change that value. But if you are talking about moving from the outside of the cell to the inside of the cell, then that is going to remain negative. So I'm going to plug this in as negative 0.09. Remember, I already did that 0.09 consideration, or that I took that into consideration previously, so I could kind of avoid, basically, what do they call it? Decision fatigue. I've avoided making a decision at this point in the problem. So I've already solved that. I knew what I was doing up here, so I'm just going to go ahead, forge ahead. So now what I'm going to do is say 0.09 times 96.485. Lo and behold, and that's multiplied by 1. And remember, we've got a negative value here and a negative value here. What's going to happen with those two negative values? Cancel one another out. So this is negative 4.149 kilojoules per mole, plus this is a positive 8.684 kilojoules per mole. And so that would mean this overall reaction is positive 4.535 kilojoules per mole. Okay, so whenever you do something, it's always helpful to think about this from the perspective of, well, was this favorable? Was this unfavorable? This overall reaction is unfavorable because we have a positive delta G value. Well, what else is happening? We are trying to move a negative ion to a space where there's already a negative charge. So this is a reaction, or this is a transport event that is unfavorable only from, or not only from, but largely resulting from the electrical potential. The electrical potential is a positive value. Hence, it's going to basically kind of deflect that ion, or it's going to resist that ion moving in. All right, so I hope this is helpful, and best wishes.